All right. Hello, everyone. We are looking at section 1.2 here, and the title of that section is Estimation, Graphs, and Mathematical Models. So let's get right into it. The process, the definition of to estimate or estimation is the process at arriving at an approximate answer to a question. Most of us have an idea of what estimating means. And so the first thing that we need to talk about within that is rounding numbers. And it's very critical for you to understand how to round numbers off as we progress through the rest of the course. And so this is a basic skill that most of us talked about originally back in elementary school. But if for whatever reasons you didn't catch it back then it has probably plagued you for every math class after that. And so let's see if you can catch it here if you have not caught it before. If you understand how to round numbers and it's easy to you or whatever, then you can skip ahead in this video and for quite a bit because I have several examples here. And so you can find where the next topic is here. But we're going to talk about rounding numbers. So the first step that you do to round a number is to find the digit where the rounding is to occur. So typically the problem will say, round this number to the nearest hundred place, or to the nearest whole number, or to the nearest tenth, or whatever. And so you find that place in the number. Okay. Then the key to rounding is looking to the digit to the right of that number. Okay. So the number to the digit to the right is the critical number that we're looking at. Okay. If that digit is less than 5, or in other words 0 to 4, then leave the digit alone, the one that we're talking about rounding. Okay. If the digit is 5 or greater, then the digit to the right is 5 or greater, then you would add 1 or round up the digit that we're talking about originally. Those are the rules right there. Okay. So let's look at an example. As an example out of your book. Around the world population, 7,058,746,857, and this first example is to the nearest 100 million. Well, the concept there is that you need to know your decimal places and know where the 100 million place is in this number. And so to find that place, it is the one next to the billion because, well, that's where the 100 million place is. And so, right, in this particular example, that's a 0. So that 0 is what we're trying to decide. Are we going to leave it a 0 or are we going to make it round it up to a 1? And so the process for doing that is that you look to the digit to the right. Okay? So the digit to the right I've put in red here. So the digit to the right is a 5. That's the one we care about to determine whether the 0 goes up or stays the same. Okay? And so because it is a 5 or greater, if it was a 5, 6, 7, 8, or 9, that means we add 1 to the place that we're caring about. And we're caring about the 100 millions place, or the 0. So we're going to add 1 to that. We're going to round it up to a 1. And then we make every digit after that a 0. Okay? Because if you're rounding, essentially you're estimating. You're approximating that number. So we have rounded this off to 7,100,000,000. And that's to the nearest 100 millions place. All right, let's look at another example. Same number, but now we're going to change the place. So now we're going to round it off to the nearest million place. So again, the first job is to find the millions place. Well, the millions place is right before the 100,000s place, or right after it, I guess, depending on which way you're looking at that. And so in this particular number, it's that 8 right there. 7,058,000,000. And so that 8 is the millions place. Okay? And so so I have it underlined here. That's the number that we're trying to decide whether we keep it the way it is or do we round it up. So again, we looked at the digit to the right. The digit to the right is 7. It's in red here. Okay, so the 7, because that's 5 or greater, we will take that number that we're caring about, the number that's underlined, the 8, and we are going to add 1 to it, or in other words, round it up, and then make the rest of the digits zeros. So because of that 7, we're going to change that 8 to a 9 and make it 7,059,000,000. All right. One more example with this particular number. Now we're going to round it to the nearest 100,000. Okay. And so again, we need to find well, that's wrong. Find the 100,000 thousands place. Sorry, that million should be hundred thousands place. The hundred thousands place is that 7 right there that's underlined. Okay, and so the 7 is there. We need to look to the number to the right, or the digit to the right, and it's a 4 this time. Now this is our first one where it's been under 5. And so because that digit is under 5, 0, 1, 2, 3, or 4, we don't do anything to the 7. We just leave it there. We don't add 1 to it. We leave the 7 the way it is, because this number is closer to 700,000 than it is to 800,000. We leave it. So we round this number off to 7,058,700,000. Hopefully that makes sense. Okay, I'm going to look at another couple of examples here, and I'm going to go through them pretty quickly. And so, but you have the advantage of pausing this video, and in fact, I may just kind of click through to the end of the slide, and then you can just pause it and see if you can follow the steps within this and see how I got to my solution. But now we're looking at pi, 3.141592, the first 7 digits of it, and we're going to round that to the nearest hundredth. Notice the th at the end, so now we're in the decimal places. So the nearest hundredths place, or the hundreds place I mean, is the 4 in that number. So I've underlined it. The digit to the right is a 1. And so because that's a 1, because it's less than 5, we leave the hundreds place and we take everything else to zeros. But when you're talking about a decimal number and you take everything to zeros, then you don't write those zeros unless you're writing it for accuracy. But there's nothing in this problem about accuracy. So we're just going to not write those zeros. Okay. So this rounds off to 3.14. Pi rounded to the nearest hundredth is 3.14. And that's the typical way we see it, 3.14. Okay. Next example, what if we had to round it to the nearest 10,000th? Well, again, we need to find the 10,000ths place. The 10,000ths place is that 5 because it goes tenths, hundredths, thousands, and then 10,000ths. So the 5 is the 10,000ths place. We look to the digit to the right of that, which happens to be a 9. And so this is closer to 6 than it is 5 in terms of the number we're looking at. And so because of that, we add 1 to the 5 and we make it 3.1416. And again, the rest are zeros, and so we just ignore them. All right? Different type of problem here. So that was our concept of rounding. If you still haven't caught that, maybe rewind and go back and look at that again. Okay? But a different kind of estimation now. So here we've gone into a grocery store and we have purchased bread for $2.59, a bottle of detergent for $2.17, a sandwich for $3.65, an apple for 47 cents, and a bag of coffee for $5.79. Total bill was $18.67 when we got up to the cash register. That's what the cashier told us that we owed, is $18.67. Is that a reasonable total? Or in other words, as you're going through the grocery store and you estimate, let's say you have a $20 bill with you or whatever, you just want to make sure you don't go over. Are you estimating what it is and that you're going to be close to that? Okay. Well, let's take each one of these and just round them off in the ways that we were just doing in the previous examples. We're just going to round to the nearest dollar. Okay. So the 259, because we're rounding the nearest dollar, that's the 2. We look to the right, that's a 5. Because it's a 5, we round up. So $2.59 is closer to $3 than it is $2. The detergent, $2.17, next digit's a 1, and so we leave the 2. In other words, $2.17 is closer to $2 than it is $3. Same with each. $3.65 is closer to $4 than it is $3, so we round up. 47 cents is closer to $0 than it is to $1, so we round it down, and that would kind of be taken care of in some of these other roundings. The $5.79 is actually closer to $6. It's really the only, well, besides the top one, I guess, that we're rounding up. It's closer to $6 than it is 5, so we're going to round it up to $6. So the key example here is we're rounding each one first. So we're going to add all those up quickly. 3 plus 2 is 5, plus 4 is 9, plus 6 is $15 that these estimates add up to. So $18.67, unless there's a high tax rate, which there isn't tax for food anyway, something's wrong here somewhere, right? And so you should be questioning the cashier. So the question here, do you question? Yes, you do question the cashier. What? Did you get something extra in there? Did you count something twice? You know, what's going on here? The actual total is $14.67, so it's even less than our estimate. And so the $18.67 is off by $4. Who knows? I don't know what went wrong, but you would have lost $4 in this process if you didn't question it. And so you just need to have those estimation skills. Okay? All right. Now we're looking at at graphs and charts and those kinds of things and trying to do some estimation with those. And so this first question is, according to the U.S. Census Bureau, in 2012, there were 229,937,770 Americans 20 years and older. Okay, so in the census, there were that many people living in the United States that were 20 years and older. Using the pie chart below that represents this data, determine how many Americans 20 and older, so how many out of that 229 million, who define old age by a decline in physical ability. Provide a reasonable estimation of this total. Well, if we look at the chart here, the chart is titled Americans' Definition of Old Age. This is how people define old age. Okay? And if you'll look in the bottom right corner, there's the one that says decline in physical ability. That's what this question talks about. Define old age by a decline in physical ability. So that represents in the pie chart 41% of the people. That's how they define old age. Okay? A decline in physical ability. So we need to come up with a calculation that estimates how many of those 20 years and older said that. Well, if 41% of the whole population said it, we're going to assume that 41% of the 20 and older said that. So we're going to take that 41% of the 229 million. So of in math means multiplication, and so we're going to multiply 41% times the 229 million number that we have up there. Okay? So that last line there, 41% of that, of means multiplication. So we're going to go 41%, which I didn't show that here, but remember to change a percent to a decimal, we move the decimal to the left 2 places. So 41% means 0.41. Percent means per 100, and so 41% is 41 out of 100, or 41 hundredths, which is 0.41. So we're going to multiply that, and we're going to get 94,274,485.7. So we're going to estimate that. We're going to round that off to be, it says provide a reasonable estimation. It doesn't say what place to take it, just a reasonable estimation. So we're going to round it off to about 94 million people that are 20 years and older define old age as decline in physical ability. That's our estimation here. Okay? Another estimation that your book shows is taking the original number, the 229 million, and rounding that off first, and rounding off the percent. So kind of like our grocery store example, where they round the two numbers first. This is a much rougher estimation. Okay, our calculation that we did originally, that would be a closer approximation, or more exact, or just a better estimation. Okay, so this example takes it to where the 41% is rounded off to just 40%, or 0.4, and rounding off the 229,937,000 to 230 million, and then doing that multiplication. You can see we're 2 million off in that estimation, and so it's a pretty severe estimating before the calculation. It's always better to do the calculation first and then estimate. So that estimation comes out to 92 million instead. Okay, but the better calculation, the better estimation is the first one that we did. All right, let's look at another example here, a bar graph estimation. It says use the data in the bar graph, and I'll pull it up in a second here, to estimate a man's increased life expectancy for each subsequent birth year, rounded to the nearest hundredth of a year. So let's see what this chart. So the chart is titled Life Expectancy in the United States by Year of Birth. So in other words, the later you were born, from 1950 on, the higher you are, the higher your life expectancy age is. Okay? So if you were born in 1950 and you were a female, say, your life expectancy was 71.1 years. Whereas a female in 2010, because of advances in medical technology and whatever, education of learning, of eating better, healthier things like not smoking, all those different kinds of things, make your life expectancy to be almost, well, it is exactly 10 years longer. That's amazing. 81.1 years. Okay, so kind of a description of what that graph is saying. Okay, but this question is, the question is, find a man's increased life expectancy for each subsequent birth year, rounded to the nearest hundredth of a year. Well, so let's look at that. You could do this a couple different ways, but the average life expectancy from 1950 to 2010, okay, and so you could take that and average it each time, or we could add the difference from the decades and average those. And that actually is probably a better calculation to make. We're going to run with the first one here. Actually, that one is the better one. Sorry, I'm getting these mixed up. But the average in life expectancy from 50 to 2010, 1950 to 2010, would be the better calculation to make. It would be more accurate because you're spreading it over a longer period of time within your calculation. You're not estimating each time first. So the life expectancy in 1950 for a male, so that's the reddish color here in the graph, is 65.6. And the life expectancy in 2010 for a male is 76.2. And so we're going to take those numbers and we are going to subtract them to find the spread over the 60 years. And that's 10.6. Okay? So life expectancy for male is 10.6 years more in 2010 than it was in 1950. That's substantial. From 1950 to 2010 is 60 years. We just subtract those also. And so we're going to do a calculation with those two numbers in it, the 10.6 and the 60 years. We're going to divide those to spread it out over those 60 years. And so 10.6 divided by the 60-year spread that is gives us 0.18. So in other words, over those 60 years, every year the life expectancy went up by 0.18 years. Okay, to add up to that total of 10.6 over the 60 years. So the question is, for each subsequent birth year, a man's life expectancy increases by that 0.18 every year. That's our estimation over those 60 years. Now, was it that much every single year? No, but that's an estimation of it over that time period. All right, let's keep with that graph, but ask another question. The life expectancy of a man born in 2020. So now they're asking us to go outside of the chart here, okay, and estimate what the life expectancy should be for a male born in 2020. So we're going to kind of do the same thing that we just did in terms of that calculation. We're going to take the 65.6 that started in 1950, okay. We're going to take that 1.8 that we calculated to be the average, well, that's incorrect. That should be 0.18. Man, I don't know why these things had not shown up on my slides before, but 0.18, or been found on my slides, 0.18 is what that should be, times 70, okay? But I believe the calculation is correct here. Okay, so each one of those, 65.6 is the average, the life expectancy for male in 1950. That should be 0.18, which is the yearly increase that we just calculated on the last slide. And then the 70 comes from the fact that we started in 1950, but now the question has 2020. So 2020 minus 1950 is 70 years now. Our last calculation was over 60 years. This one's over 70 years. So my decimal point there in the life expectancy is the only thing incorrect here. And so that takes it to 78.2. So even though I wrote 1.8, I calculated it with 0.18. And so in the 2010 graph, it was 76.2 life expectancy. So it's going to go up exactly 2 years, estimating, in 2020. So a male born in 2020 will have a life expectancy of 78.2 years here in the U.S. Okay. Let's go to a line graph, and this one is kind of done in the graph, in the picture itself. But anyway, this graph is of women's average age for their first marriage. Okay, how old is a woman on average the first time they marry? And so the question here specifically though is, what is the average age for a woman to marry? What was the average age for the average woman to marry in 1980? Well, again, it's kind of done already here for it. 1980, we just go up to the line graph here, and corresponding Y value of that, or the age value of that, was 22. Therefore, the answer to the question comes directly from the graph. We don't need to do a calculation of any kind. It comes directly from the graph. The average age in 1980 was 22. And if that dot were to fall, like if the question was 1983 or something like that, you would just have to do your best estimation of that, okay, from the graph itself, if it didn't hit right on one of the corners of boxes, okay. Mathematical models is our last topic for this section. Mathematical models is really, a mathematical model is just an equation. It's a function, an equation or a rule that describes what's happening in this graph, okay. So first of all, let's look at this bar chart here. It's the average cost of tuition and fees at a public four-year U.S. college, okay. So a public four-year college here. So since 2000, from 2000 to 2010, they have increased substantially. Man, that's crazy. $3,362 was the average cost in 2000 for tuition and fees, and just 10 years later, in 2010, that more than doubled, right? $7,020 for tuition and fees. That's a huge increase. So our question here is estimate the yearly increase in tuition and fees. So we want to know how much it's gone up on average each year for that amount, and round it to the nearest dollar. So we're going to take the amount that it ended with, the 7,020, we're going to subtract the amount that it started with, kind of like we did with our years in the last two examples. So we're going to take $7,020 in 2010, subtract the $3,362 it was in 2000, because that's how much it's gone up over the 10 years, whatever that subtracts out to. Then 2010 minus 2000 is the number of year span that takes, just like we did in our last couple of examples, or the previous examples of the life expectancy and so on. We're just going to subtract the years. So if we do those subtractions and division, it comes out to 365.8, and it says to round to the nearest dollar. And so it says each year the average cost of tuition in a four-year U.S. college, public college, was $366. We just took that 365.8, rounded it up, $366. So on average, every year, it went up $366. Okay. Now, obviously, you can see in the chart that some of the years it jumped considerably more than that. Okay, but that's the average. So the question is, based on that, write a mathematical model that estimates this increase. Or in other words, again, like if we wanted to kind of like our previous second example earlier, if we wanted to estimate what is it going to be in 2020 then, well, we need a formula to plug that into to be able to calculate that. So here is the formula, okay, but let's see where these pieces came from. So the T is, we could use whatever variable you want to use. T just stands for tuition. You could call it C for cost. You could call it whatever you want to call it, okay? So some variable, I'm going to call it T for tuition, equals, which is in the English version of the question, right? The 3362 is the original cost from our chart. So that's where we started from, okay? So we start with that base, and then we're going to add a certain amount every year after that, on average. Okay, we're estimating here. So we're going to add to that a yearly increase, which we just calculated to be $366 on average. If this curve continues along the way that it has been, then on average, that's how much it's gone up every year. And then X is the number of times that, or number of years since 2000. So in our particular example that I was saying earlier, not on our chart here, but on the slide, but let's say they asked us what it is in 2020, or what you estimate it to be in 2020. Then you would plug 20 in for that X right there, multiply it by the 366, because that's the average annual, and then add it to the baseline of the 3362. So there's our mathematical model. T equals 3,362 plus 366X. Give us any year, we can calculate approximately what the tuition cost was in that year. All right, so that is our section 1-2 video. Now you need to go in and do that homework section 1-2 in MyMathLab and go from there. If you come up with questions that doesn't help with, then just email me. Thanks.